Welcome to today's paper reading. Today's paper is titled, Integer Value Training and Spike-Driven Inference Spiking Neural Network for High Performance and Energy-Efficient Object Detection. This paper was published on AR14 by Xinhao Luo and colleagues from the Institute of Automation, Chinese Academy of Sciences. The abstract highlights the bio-plausibility and low-power advantages of spiking neural networks, SNNs, over artificial neural networks, ANNs. However, the application of SNNs is currently limited to simple classification tasks due to poor performance. This work addresses the performance gap in object detection by introducing the SpikeYOLO architecture, which simplifies the vanilla YOLO and incorporates meta-SNN blocks. The new spiking neuron design activates integer values during training and extends virtual time steps during inference. The proposed method achieves significant improvements on both static and neuromorphic datasets, with 66.2% map at 50 and 48.9% map at 50:95 on the COCO dataset, and 67.2% map at 50 on the Gen 1 dataset. Brain-inspired spiking neural networks, SNNs, are renowned for their low power consumption due to their ability to process spatio-temporal information and perform sparse additions. However, SNNs face challenges such as complex neuronal dynamics, limited task performance, and difficulty in training. To address these issues, the authors introduced SpikeYOLO, a novel architecture that combines the macro design of YOLO with the micro design of SNN modules. This approach simplifies the complex YOLO V8 architecture and incorporates meta-SNN blocks to enhance performance. In the realm of spiking neural networks, SNNs, training methods have historically posed significant challenges. Two primary approaches have emerged, ANN-to-SNN, which replaces ReLU functions with spiking neurons to mimic continuous activation, and direct training, which uses gradient surrogates to handle the non-differentiability of binary spikes. The latter is preferred in this work for its architectural flexibility. SNN architecture design is divided into CNN-based, dominated by spiking ResNet, and transformer-based, with metaspikeformers setting new performance benchmarks. The SpikeYOLO architecture combines elements from both. Quantization errors, inherent in SNNs due to the binary nature of spikes, are managed differently in ANN-to-SNN and direct training. This work employs integer values during training to mitigate these errors. Object detection, a critical task, is challenging for SNNs, with existing frameworks falling into two-stage, RCNN series, and single-stage, YOLO, data series, categories. Few SNN-based object detection works exist, highlighting the need for further research. SpikeYOLO is designed to process both static and neuromorphic object detection datasets. It integrates the YOLO V8 architecture with the metaspikeformer designed to address issues of spike degradation when converting to SNNs. The network input for static images involves direct input encoding, while neuromorphic data is processed through event-based streams. The architecture includes two SNN blocks. SNN Block 1 uses standard convolution, and SNN Block 2 employs reparameterization convolution. The ILAF spiking neuron is used for integer value training, which reduces quantization errors. Figure 1 provides an overview of the SpikeYOLO architecture, which is designed for high-performance and energy-efficient object detection. The architecture includes two types of SNN blocks, SNN Block 1 and SNN Block 2. SNN Block 1 employs standard convolution within its channel CONV component, while SNN Block 2 utilizes reparameterization convolution. This distinction in the channel mixer module is crucial for feature extraction at different stages. Additionally, the spiking neuron used in this architecture is the ILAF neuron, which activates integer values during training to reduce quantization errors, while during inference, it converts these values to binary spikes to maintain the low-power nature of SNNs. Figure 2 illustrates the difference between the ILAF and LIF spiking neurons. The LIF neuron emits binary spikes both during training and inference, which can lead to quantization errors. In contrast, the ILAF neuron emits integer values during the training process to minimize these quantization errors. During inference, ILAF converts these integer values into binary spikes, ensuring that the network performs sparse addition operations. This approach aims to balance the need for accurate representation during training with the efficiency of binary operations during inference. Figure 3 illustrates the operation of the proposed ILIF during inference. It assumes a time step t of 3 and a maximum integer value d of 2, demonstrating the conversion of integer values into binary spike sequences. The membrane potential is quantized. Values between 0.5 and 1.5 are set to 1, and those between 1.5 and 2.5 are set to 2. Any potential above 2.5 is also quantized to 2 due to the limit set by d. This quantization process is followed by the subtraction of the integer value from the membrane potential. During inference, a training spike with a value of 2 is extended into 2 binary spikes by utilizing virtual time steps. On the COCO 2017 dataset, SpikeYOLO achieves 66.2% map at 50 and 48.9% map at 50:95, representing a significant improvement over previous state-of-the-art SNNs by plus 15.0% and plus 18.7%, respectively. On the Gen 1 dataset, SpikeYOLO attained 67.2% map at 50 with 23.1 M parameters, outperforming the prior state-of-the-art SNN by plus 8.2%. SpikeYOLO demonstrates notable energy efficiency, with a 3.3 times improvement compared to ANNs under similar parameters, and a 5.7 times energy efficiency on the Gen 1 dataset. These results indicate that SNNs, particularly SpikeYOLO, have a promising future in object detection tasks, especially when dealing with neuromorphic data. Figure 4 presents the object detection results on the COCO dataset, focusing on 2 main comparisons. The first 2 columns illustrate the impact of varying the maximum integer value d on performance for a fixed model structure. This analysis reveals how changes in d affect the detection accuracy. The second and third columns then shift the focus to the effect of the model size on performance. Here, the comparison highlights the trade-offs between model complexity and detection effectiveness. Overall, Figure 4 provides a comprehensive view of how different parameters and model sizes influence object detection performance on the COCO dataset. Table 1 presents the results of various models on the COCO 2017 validation dataset, highlighting the performance of SpikeYOLO. The table shows that SpikeYOLO significantly improves upon previous state-of-the-art SNNs in terms of mean average precision at IOU equals 0.5, map at 50, and the average map between 0.5 and 0.95, map at 50:95. SpikeYOLO also demonstrates advantages in reducing the number of parameters and power consumption compared to other SNNs. Additionally, the table indicates that increasing the value of d, the upper limit of integer activation during training, is more effective in reducing quantization error than increasing the number of time steps t, leading to better performance and more cost-effective power usage. Table 2 presents the results of ablation studies focusing on architectural design. The study involves converting YOLO V8 directly into its spiking version and then converting the SpikeYOLO designed in this work into its ANN counterpart. The key findings indicate significant performance degradation when directly converting ANN architectures into SNNs, highlighting the importance of specialized architectural design for SNNs to enhance their representational capabilities. Table 3 presents the object detection results on the Gen 1 dataset, highlighting the performance of SpikeYOLO in comparison to other models. Key findings include SpikeYOLO achieving a 67.2% map at 50 with 23.1 million parameters, outperforming previous state-of-the-art SNN models by 8.2%. Additionally, SpikeYOLO demonstrates a 5.7 times higher energy efficiency compared to its ANN counterpart, indicating the potential of SNNs in processing neuromorphic data. Table 4 presents a comprehensive ablation study on SpikeYOLO with 23.1 M parameters, evaluating the effects of varying T and D on the Gen 1 dataset. Key findings include: increasing the time step T from 1 to 4 results in a plus 6.7% increase in map at 50 and a 3.7 times increase in power. Expanding D at a fixed T improves performance while reducing power, exemplified by the comparison of 2:1 versus 2:2 versus 2:4, showing map at 50 of 63.6% versus 66.1% versus 67% and power of 8.1 mJ versus 7.8 mJ versus 7.1 mJ. This trend contrasts with SpikeYOLO's performance on the COCO dataset, where increasing D typically increases energy cost. Table 5 presents the results of ablation studies on the SpikeYOLO architecture design. The study focuses on how modifications to the baseline architecture, with T times D set to 1/4, affect parameters, power consumption, and performance metrics such as map at 50 and map at 50:95. Key findings include a 1.7% decrease in map at 50 when reparameterization is removed, a 1% drop when SNN block 1 is replaced with SNN block 2, and a significant 2.8% reduction in map at 50 when switching from an anchor-free to an anchor-based detection head. These results highlight the critical role of specific architectural components in maintaining high performance in SpikeYOLO. The SpikeYOLO architecture simplifies the design by using meta-spike blocks, which improves the performance of SNNs. The YOLO spiking neuron model supports integer value training and spike-driven inference, effectively reducing quantization errors. These innovations have led to significant performance improvements on the COCO dataset, with increases of 15% in map at 50 and 18.7% in map at 50:95. Additionally, SpikeYOLO demonstrates superior performance and lower power consumption on the neuromorphic Gen 1 dataset compared to equivalent ANN architectures. Thank you for watching.